So next we have Ricardo Domingues from the University of Miami's Cooperative Institute for Marine and Atmospheric Studies at NOAA's AOML lab. Ricardo, are you going to try and present yours? There you go.
Yes. I assume you can all see my screen.
Yep. Welcome.
Okay.
Go ahead when you're ready.
All right. Well, good afternoon, everyone, and thanks for having me. First, I would like to take this opportunity to acknowledge my co-authors and also our AOML glider team members, because some of the findings that I will present here, they are only possible thanks to the work of a large team, which also include many moving parts for making our hurricane operation happen. And I also want to take this opportunity to thank the support from the Improving Forecasting and Assimilation portfolio. So moving right into it, we started our AOML hurricane underwater glider operations with one of the key objectives being carrying out underwater glider observations in real time to support hurricane intensity forecast. Here's a brief overview of the observations that we have done since 2014. We have collected over 35,000 temperature and salinity profiles in areas where hurricanes commonly travel and intensify in the Caribbean Sea and tropical North Atlantic. And this data set actually includes very unique observations sampled from several tropical cyclones. And some of these data sets, for example, for Hurricane Gonzalo, allowed us to, for the first time, to quantify and confirm that indeed the assimilation of ocean observations can have a substantial impact in improving hurricane intensity forecasts. And now we'll explore that a little bit further now for hurricanes Irma, Jose, and Maria. So we focus on these three hurricanes because they had a very similar synoptic history. They originated off tropical waves of the West Africa, and the three hurricanes, they travel over similar ocean regions in the North Atlantic Ocean and Caribbean Sea. So you can see that these are some of the baseline conditions derived from satellite observations. These areas, they were actually characterized by large SSTs with values between reaching values of 28 to 30 degrees Celsius. And on top of that, we had a very large upper ocean heat content as well, sometimes reaching values as large as 100 kilojoules per centimeter square, which is way beyond the threshold that is generally required for intensification of 50 kilojoules per centimeter square. And on top of that, we also had a very widespread low salinity plume associated with the Amazon and Orinoco river plumes. And this is important because we know that these freshwater plumes, they have the potential of creating barrier layer conditions, which essentially is an increase in the vertical density stratification, which suppresses the mixing force by the hurricane and help maintains the SST warm. So with that, they help fuel the hurricane. And what was curious about these three hurricanes is that they actually intensified and reached their peak intensity in the areas where these three conditions overlapped, as you're seeing here through this very simple schematic showing the overlap of these three ocean conditions and the peaking hurricane intensity. And we happen to have three of our AOML gliders in the area during the passage of these three hurricanes. And the data sets collected by these three gliders allowed us to look into the details of the upper ocean interaction with these three hurricanes, not only before, but during and after these storms as well. So, and here's a brief overview of some of the data sets that we collected. On the left, you're seeing a pre-storm profile sampled in the vicinity of where Maria traveled. You can see that in the profiles in red are the profiles right before the passage of the hurricane. So what these observations show is that they actually confirm that indeed we had a very warm upper layer with temperatures above 26 degrees occupying over the top 120 meters of the water column. And we also had a very pronounced low salinity conditions near the surface, creating that barrier layer conditions. So on the right here, we're summarizing the ocean response to these hurricanes. This is basically in terms of the barrier layer conditions and the SST cooling. And here's the time evolution as these three storms approached the location of our gliders. And I wanted to emphasize two key points here. So the first one being that as these storms approach, you see the partial erosion of the barrier layer conditions, which is expected because of the mixing force by the hurricane. But really the main point here is that, as you can see, the SST cooling forced by the hurricanes was actually smaller than 1 degree Celsius. And that is important because those pre-existing ocean conditions helped maintain the SSTs warmer than 28 degrees Celsius throughout the passage of these three hurricanes, which we know is way beyond the threshold required for hurricane intensification. And therefore, we can say that these conditions likely contributed to sustaining and favoring their further intensification. Notice here how I'm emphasizing the word likely, because up to here, we haven't actually quantified that. And so we want to address these two questions to show how they actually contributed. So first, how much did these ocean conditions actually contributed to the hurricane intensification of these three hurricanes? And second, what is the specific contribution of different components of the ocean observing system to improve these intensity forecasts? And so in order to address these questions, we take advantage of our capability of performing ocean observing system experiments, or OSES for short. So essentially, with OSES, we can carry out different simulations by assimilating different components of the ocean observing system separately, but also quantify their impact of their combined contribution to the forecast. So we carried out these 5 OSES experiments, one being without any assimilation of ocean observations, and then we subsequently started including observations. And then we also had we call the control experiment, which we assimilate all ocean observations available. And we use those as initial conditions for the couple hurricane model, HWRF-HICOM, which is one of the state-of-the-art semi-operational models within NOAA. And we carry out several forecast cycles for these OSES, for these different OSES. And with that, we can derive some robust statistics of the actual impact of these observations. So we'll first just focus on the comparison between no ocean observations and all ocean observations, just to provide you with a sense of the actual impact of having a realistic ocean in the model. And before that, let me just go here and explain to you what is the actual impact of assimilating the ocean observations in the ocean. So what you're seeing in this slide is the errors in the model with respect to satellite observations on the left, and then to underwater glider observations on the right. And they're quantified in terms of error in SST and in tropical cyclone heat potential. So as you can see here, when we have no ocean observations assimilated, we tend to have cold biases in the model. And those biases, they appear not only in SST, but mostly as a cold signature in the upper ocean heat content. And when we look at the subsurface conditions, you can see that most of the upper ocean is actually way cooler than what the observations are showing. There are values here as cold as 3 degrees colder than what the observations are showing. And when we assimilate the ocean observations, you largely reduce those initial errors in the forecast. And as you can see here, as the surface expression, and then here in the subsurface as well. And this is important because here's the time series of the evolution of the coupled forecast, and that these errors, they persist through the initial errors. They will be observed to persist throughout the forecast. And so one of the key points here is that without ocean data assimilation, we will tend to have cold temperature biases in the upper ocean. And this is important. And this is what actually the impact that translates into the intensification. So this is an example of one single forecast cycle for the forecast with no ocean observations here in blue, and then with ocean observations in red. So you can see that by having a more accurate representation of the upper ocean, we were able to improve this single forecast cycle by up to 25%. That is solely because we have a better representation of the ocean. And so, and why does that come to be? This is an example of the hurricane structure associated with those coupled forecasts. So on the left, you're seeing the total enthalpy fluxes for the experiment with all ocean observations assimilated, and then on the right, when no observations were assimilated. So essentially, by having a more accurate representation of the ocean, we are able to better reproduce these enthalpy fluxes, and with that, we can have a better representation of the hurricane itself. So those results, they were for a single forecast cycle, but with our experiments, we were actually able to derive some more quantitative statistics. So this is a time series of the RMS error evolution considering all forecast cycles for the different ocean observing system experiments. So you'll see here, and these are the actual average statistics for these 3-day forecast of Maria. So when we don't have ocean observations for Maria, we obtain an RMS error of 23 knots for no ocean observations assimilated, and we improved by 20% that just by assimilating all ocean observations available. And the key point I wanted to make here is that as you include different components of the ocean observing system, you're progressively improving these coupled forecasts. So the impact is always positive. You may be wondering here, with gliders, we obtain a very subtle improvement in the skew of the forecast. Well, this is largely because the 3-day forecast that we're considering here actually include ocean areas that are way beyond of the area where we had the actual glider observation. So this is not a very fair assessment of the impact of gliders. So a much more robust quantification for this is actually considering the 24-hour before landfall. And when we do that, you can see that overall, we had, just for this time frame, we had a 30% improvement in the forecast with respect to the simulation with no ocean observations assimilated. And most importantly, gliders provided the single most contribution to the improvement in the skew of the coupled forecast of Maria. So this is important because we will generally have gliders surveying areas that are actually closer to land because of the logistics of the deployments. And so gliders, what this shows is that gliders provide us with an opportunity to greatly improve the forecast for the critical time frame right before landfall. And I also wanted to make a point here that in 2017, we only had 3 gliders in the water. So thanks to the collaboration put forward last year, where we had, here I have it 32, but we just learned that we're close to 40 deployments. And just in the area where Maria traveled, we had over 10 gliders in the water surveying this area. So it's a fair point to say that had Maria occurred in 2019, we would likely see a much larger impact of glider observations in helping improve the forecast of Maria. So as conclusions, I'm just go over quickly here. So we did see some pre-existing ocean conditions that help maintain the SSTs warmer throughout the passage of these 3 hurricanes, which contributed to sustaining and favoring their further intensification. We saw that assimilation of ocean observations enabled an overall 20% improvement in its 72-hour forecast of Maria. And I didn't show this, but this is one point that we learned from our simulations, is that altimetry generally helps resolve the mesoscale features, but it doesn't correct for the subsurface temperature biases. In other words, we will have a better representation of the mesoscale circulation, but we will still have the cold biases in the upper ocean. And that's largely because of the data simulation algorithm used for altimetry. And in order to correct those, you really need profiling floats observations. And glider helps resolve those subsurface biases, but also the horizontal gradients and high resolution salinity features, which George showed very nicely in his presentation. And so having the correct representation of the upper ocean will enable a more accurate simulation of the enthalpy fluxes, and with that we can obtain better forecasts. And as I said, and as I just said, the gliders, they can provide these great opportunity to help improve the forecast right before landfall, as we saw for Maria. And with no data simulation, the couple models, they generally tend to be too cold to sustain a further intensification. And finally, Mathilde will also show some very exciting results from similar experiments carried out in the Gulf of Mexico for Hurricane Michael. And so with that, we have a paper with some of these results currently submitted and awaiting for monthly weather review, and it's currently under revision. Thank you very much.